In this lesson, we will try to analyze time complexity of recursion to calculate x to the power n. In a previous lesson, we had seen two different recursive approaches to calculate x to the power n. We will try to reduce time complexity for both of them mathematically. Now, the first approach that we had seen was this. We had defined a recurrence relation where we had expressed x to the power n as x into x to the power n minus 1, and n is equal to 0 was our base condition. So in the program it goes like, if n is 0 then simply return 1, else make a recursive call to calculate x to the power n minus 1, multiply it with x and return the output. Now once again, when we try to analyze time complexity, we say that each simple operation costs us 1 unit of time. So any of the arithmetic operations like addition, subtraction, or a comparison, all of these cost us 1 unit of time. Now in this particular program, as you can see, there is a comparison. Let's say it takes 1 unit of time. So if n is greater than 0, then we first compare it with 0. Then we make a recursive call and we make a subtraction to pass the argument. So this is 1 unit of cost, and this multiplication is say 1 unit of cost, and let's say all other costs are negligible. Then if we were not making a recursive call, then the cost would have been only 3 units, or the cost would have been some constant. But because we are making a recursive call, the time taken varies. Now it should also be evident to you that the time taken does not vary because of x. It varies only because of n, because it is n that is deciding that how many times the recursion would be called, or what would be the depth of the recursion tree. So for example, if we want to calculate x to the power 4, then we go on making recursive calls like this. So we have 5 calls in calculation of x to the power 4. Similarly, in calculation of x to the power 2, there would be 3 calls. So the time taken by this program is only a function of n. So let's say time taken is Tn for an input n. So Tn would be equal to the time taken to calculate x to the power n minus 1, which will be Tn minus 1, plus some constant time. Let's say it's equal to c for these simple operations like comparison and multiplication and subtraction, and this is true for all n greater than 0. And for our base case, which is t0, there is just one comparison with 0 and a return. So let's say this is 1 unit of time. Now let's try to solve this recurrence relation and try to express it in terms of the base condition, which is t0. Now this is pretty straightforward. Tn minus 1 can be written as Tn minus 2 plus c, so this will be Tn minus 2 plus 2c, and we can go on like Tn minus 3 plus 3c, or if we want to write it some generic form, then Tn minus k plus k into c. Now we want to express this in terms of t0. So in that case, n minus k will be equal to 0. That will imply k will be equal to n. So eventually Tn will be equal to t0 plus nc, where c is a constant, and t0 is nothing but 1. So this will be nc plus 1 overall. So clearly the time taken is proportional to n, and this is also big O of n, or order of n, in terms of time complexity. Now let us try to analyze the second approach to calculate x to the power n. So this time we had expressed x to the power n as x to the power n by 2 into x to the power n by 2 if n is even, x into x to the power n minus 1 if n is odd, and 1 for the base case, which is n is equal to 0. And the program goes something like this. If n is 0, return 1. If n is even, calculate x to the power n by 2 and return its square, else make a recursive call to calculate x to the power n minus 1 and return the product of it with x. So again, like the previous case, the time taken is a function of n and it does not depend upon the x in this case as well. Let's say the time taken is Tn. Now if n is even, then we make a recursive call to calculate x to the power n by 2. So we can say that Tn is equal to Tn by 2 plus some constant time for the simple operations like comparison, division, or modulo. So let's say this constant is C1 this time, and this is true if n is even. If n is odd, then we make a recursive call to calculate x to the power n minus 1. So Tn would be Tn minus 1 plus some constant time for the simple operations. Let's say this constant time is C2. And for the base case, we have T0. There is just one comparison. So let's say this takes 1 unit of time. Now if n is odd, then n minus 1 must be even. So for the second case, when n is odd, we can also write this as Tn minus 1 by 2 plus C1. So for the odd scenario, Tn can be equal to Tn minus 1 by 2 plus C1 plus C2. Now if n is an integer and we take only the integral part, then we can also write this as Tn by 2. Tn minus 1 by 2 is Tn by 2 if n is always odd. And we can write this C1 plus C2 as some other constant C. And this is similar to even case, except that the constant has changed. And because C is greater than C1, so this solving this particular recurrence relation will give us an overall analysis of the upper bound of the time taken, which is fine because we often analyze the closest upper bound of the time taken in complexity analysis. Now let us try to reduce this expression. Tn by 2 can be written as Tn by 4 plus C. So this will be Tn by 4 plus 2C, and we can go on reducing like this. We can write this as Tn by 8 plus 3C, and if I have to write it in some generic form, then this can be written as Tn by 2 to the power k plus k into C. Now if n is a positive integer and if we go on dividing it by 2, so if we go from Tn by 2 to Tn by 4 and Tn by 8 and so on, we can never reach T0. So let us define one more base case here. Let's define T1, and this will be equal to 1 is odd, so this will be equal to T0 plus 1, and T0 is nothing but 1, so this will be 1 plus C2 by this particular recurrence relation here. Now let us try to express Tn in terms of T1. In that case, n by 2 to the power k will be equal to 1. That will imply 2 to the power k is n, or k is log n to the base 2. So Tn can be written as T1 plus C log n, where C is a constant and T1 is also a constant, which is equal to 1 plus C2. So the overall expression is 1 plus C2 plus C log n, where C and C2 are both constants. So we can see here that time taken Tn is proportional to log n. So this is a big O of log n algorithm, or order of log n algorithm, in terms of time complexity. Now there was a similar problem that we had solved, which was to calculate modular exponentiation, and in that problem also we solve this same recurrence relation. Tn is equal to Tn by 2 plus C. So the complexity for that algorithm is O log n as well, and order of log n is the best time complexity to have. Thanks for watching.